Since light is a wave, the Doppler effect will apply. And it's actually easier for light because it doesn't matter whether it is the source or the detector moving. All that matters is the relative velocity between the two. In the equation, we have the frequency that the observer sees is the frequency given out by the source times 1 plus or minus their relative velocity over c. And so we use the plus sign if the source is coming closer to the detector, and that means its frequency will be greater. But if it is receding, then we use the minus sign because the frequency is lower. Now, we usually show Doppler shift for light in terms of wavelength rather than frequency. And so the equation that you mostly use is V over C equals delta lambda, which is the wavelength shift, divided by the wavelength of the source at rest. So here the quantity delta lambda is sometimes called just the wavelength Doppler shift. So the equation here simply gives you the magnitude of it, and you have to remember that if the light source is approaching, the wavelength has to be shifted to be shorter, so it will be lambda naught minus delta lambda. But for a light source moving away, its wavelength gets shifted to be longer, and so that will be lambda naught plus delta lambda. And this is called redshift, of course, because the long wavelength means the red end of the visible spectrum. One thing about Doppler shift is that it only lets you measure the component of something's velocity that is moving towards or away from us. If something is moving but across our line of vision, then we don't get any Doppler shift. The Doppler effect is used to detect when stellar light sources are moving closer or further away. One application of this is in detecting exoplanets, which are planets orbiting other stars. It's called the radial velocity method because it lets you find the maximum velocity towards or away from us. It's also called the Doppler wobble method because it works like this. If a planet is orbiting a star, then they're both exerting gravitational force on each other, which means that they both circle around their joint centre of mass. The planet is a lot smaller than the star, so the centre of mass is generally somewhere actually inside the star. So the planet orbits, but the star seems to wobble. Now, if the star is wobbling towards us and away from us, we will see slight shifts in its spectrum. When it's moving towards us, the wavelength will be shifted to be slightly shorter, and as it moves away, the wavelength will be slightly longer. Looking at a graph of wavelength versus time, you can actually find the orbital period of the planet, and hence work out its distance from the star. Now, about a third of exoplanets have been found by this method, but it has what we call a selection bias, which means that it doesn't really pick out all kinds of planets that can exist. What it tends to find is the ones that they call hot Jupiters, and that means planets that are very close to the star, so they're very hot, and planets that are very, very large, about the size of Jupiter, because these are the ones that will make the most obvious wobble in the star that they're orbiting. When we look at the structure of the universe, we see galaxies moving away from us. The wavelength shift that we use to describe this is called redshift, not Doppler shift, because it isn't the galaxies themselves that are moving, but more that the space that the galaxies are in is expanding. Now, you can see this with the fruit bun analogy that is at the bottom right. So the sultanas represent the galaxies within the universe. The sultanas aren't actually moving within the bun, but the bun itself is expanding, so the sultanas are becoming further apart. So we take redshift as evidence that the whole universe is expanding. Hubble found a linear relationship between the distance of a galaxy from us and its speed away from us. This relationship is called Hubble's law, and it is what astronomers use to estimate the age of the universe. If you want to find out more about this, you can look at our free depth study resources for a Year 11 project on Hubble's law. Now, the equation here for the redshift, and Z is described as the redshift, is different from the equation you saw in the last slide for the wavelength shift. That is because the previous one was an approximation for relatively low speeds, but these galaxies that they can now observe are so far away from us that they are moving extremely fast, and we have to take into account relativistic speeds. So the equation you see there is the one that we have to use for speeds that are a sizable proportion of the speed of light. And just for your interest, the fastest object that they have found to date has a redshift of 11.09, and if you plug that into the equation, you will find that that means its speed is about 0.98 times the speed of light.